Welcome everyone to the 2026 Photonics Spectra Summit Series. Thank you so much for attending the Optical Fabrication Summit. And in this session, you'll hear from Caroline Martinez, an innovation group leader at Pureon. Caroline earned a master's degree in chemical engineering and has spent the last 4 years developing consumables for the grinding and polishing of precision optics and other semiconductor materials. Today, she joins us to help overcome the processing and polishing challenges of calcium fluoride precision optics. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all from me. Caroline, we appreciate you for taking the time to join us here at the Optical Fabrication Summit.
Thank you, Jacob, for the introduction. So today I'll be presenting overcoming processing and polishing challenges in calcium fluoride precision optics. I'll start off with an introduction to Pureon and then go into the purpose and background of this study, and then go into the experimental details and then the results. So to start off with an introduction to Pureon. So our commitment is that we are a vertically integrated surface solutions provider, and our solutions are backed with in-house product development, research, and application testing along the entire value chain. Our global presence in manufacturing and research ensures that we're closer to the customer to support their application development needs. We strive to be the global go-to provider of surface finishing solutions for high-tech materials. Across the globe, we have locations in Europe, North America, and Asia. We have our headquarters in Switzerland, production in Germany, the United States, in China, and a sales office in Japan, where we serve customers in more than 40 countries across those continents. We have surface finishing solutions for every step along the way for processing high-tech materials, from cutting to grinding to lapping to polishing to CMP. We have solutions for a wide range of materials such as silicon, sapphire, ceramic, silicon carbide, optical materials, and others. Our contribution is that we have slurries for wafer slicing and wire sawing, diamond powders and liquid diamonds, lapping and polishing slurries, grinding pads and polishing pads, and compounds. Now I'll go into the purpose and background. So the purpose of the study was to develop a fast polishing process of calcium fluoride to remove the damage from grinding while achieving low surface roughness during bulk and intermediate polishing. Why were we interested in calcium fluoride? We were interested in calcium fluoride because it is compared to other optical materials, it has a broad transmission range for ultraviolet and infrared transmission, as well as low absorption, high damage threshold, thermal resistance, and low refraction index. Some interesting applications for calcium fluoride includes a laser system, UV and excimer lasers used in micromachining or defense-based laser systems, spectroscopy for both IR and UV spectroscopy. Aerospace can be used in high altitude and space-based instruments, as well as thermal imaging. For the common manufacturing process for optics, we have outlined here. You usually start off with generating your optic, and then you go into grinding in order to get the certain thickness that's needed for the application. And then after grinding, you do lapping or an intermediate polish to remove the damage from grinding. And then after the lapping or intermediate polish, you can go into final polish to remove the damage from the previous steps, as well as to get the surface roughness needed for the application. But each of these, when you go from finer polish to finer polish, each step gets, you can get a more precise surface, but a slower rate. So balancing material removal rate and surface roughness in each of these steps is important to have an optimized process. So for calcium fluoride's physical properties, we're interested in processing this because it is different than the common optical materials that we're used to polishing. So because of that, the typical polishing solutions do not work for calcium fluoride. That would work for very common materials like fused silica and BK7. Calcium fluoride also has a crystalline structure. So we have some physical properties outlined here. So as you can see with the Knoop hardness, it is a much less hard material or softer with 158 Knoop hardness versus fused silica that is 570 and BK7 is 610. Another key difference is the crystalline structure, where calcium fluoride is crystalline versus fused silica and BK7 are not. As well, it has a much higher thermal expansion coefficient. The product that we have found that works well with polishing this different type of material is called ultrasol alumigem. The alumigem is a platform that utilizes both precisely graded diamonds and alumina abrasives dispersed and suspended in optimized carrier fluid for the bulk and to final polishing steps, where you choose a different diamond size depending on the different polishing step you're on, with using like a larger diamond for the first step after grinding for bulk removal, and then stepping down to smaller diamonds. We tested 3 different pads in this study: MHS, which is a polyurethane pad with a microcellular pore matrix with a low compressibility of 3% and a high hardness of 84. For this pad, we had it XY grooved. We used Suba 4, which is a polyurethane impregnated felt pad, non-woven, which has a higher compressibility of 13% and a lower hardness of 44. And then the Polytex, which is a soft pad, vertical pore structure, and compressible substrate with a compressibility of 14.75%. I will now go into the experimental details. So this outlines our process parameters and the material that we use. So we used calcium fluoride, and the samples were 50.8 millimeters or 2 inches in diameter, and was for IR application specifically from Crystron. And the initial thickness was 3 millimeters, and that were previously ground. The tool we used was the Lapmaster 12, where the platen speed was 40 RPM and the arm speed wheel was 100 RPM. We used our NTA templates to hold the workpiece, and the slurry was varied, but we used 500 milliliters undiluted and recirculated for each step, and the flow rate was 40 mils a minute. The material removal rate was calculated using mass change. The experimental conditions were for the intermediate polish. We tested the MHS pad with a 3-micron alumigem with the tool and the template were the same for both. For puck weights, for the sample holder were 5 pounds and 1 pound, which equated to 1.6 psi for the 5-pound puck and 0.3 psi for the 1-pound puck. The final polish, we tested MHS, Suba 4, and Polytex with a 1/4 micron alumigem on the same tool and template. And then the puck weights were 1 pound, which was 0.3 psi, and then 0.3 pounds for 0.1 psi. We measured the surface roughness with the Z-Gauge Pro HR, which is a coherence scanning interferometer that takes images that shows a 3D optical profile of the sample. We tested 3 different points: center, mid, radius, and edge, and then we averaged these values and to get a full picture of the surface. And then we also used the minimal form removal, which we used cylinder form removal. Now I will go on to the results. So for the 3-micron alumigem step, we used the 2 different pressures of 0.3 psi and 1.6 psi on MHS, And what we found was that their material removal rate was over 3 times faster at 1.6 psi versus 0.3 psi, and there was not a significant difference in surface quality. So the material removal rate at 0.3 psi was 10.2 microns an hour, and the material removal rate for 1.6 psi was 30.7 microns an hour. And then for surface roughness, the SA was 6.85 at 0.3 psi and 6.68 for 1.6 psi. And we see that for the other surface roughness values where it is slightly better for the 1.6 psi for the root mean squared, or the SQ, it was 8.6 versus 8.51 nanometers. And then for the SC, or the peak to valley was 88.2 or 80 nanometers for the SC. And then we have progression of the 3 micron step. So the samples from the ground step had subsurface damage that was quite deep. And here we can see how the surface improves as you remove material. So for the ground sample, the SZ, or the peak to value, started at over 5,000. So there's these very deep damage from the ground step, where the SQ, or the root mean squared, was 500 nanometers, and the SA was 360 nanometers. The 3 micron, after 3 microns being removed, we saw that the surface improved greatly, with the SA going down to 13 nanometers. But you can still see the peak to valley is still quite high at over 1,000. So you can kind of see there's these little pits here that are still from the ground damage. And then at 15 microns removed, again, the peak to value reduced by almost half again. And then after 20 microns removed, it was completely clear of the ground damage, where the SA ended up being 5 nanometers, and the SQ 6 nanometers, and the SC down to 56 nanometers from 5,000. So for the quarter micron aluminium step with different pads at 0.1 psi, the MHS had a material removal rate of 3.5 microns an hour, and the SC was increased to 11 nanometers, and the SC increased from like 50 from the previous step to 400 nanometers. So we can see here that there's some damage being introduced by using the MHS on this step, with these deeper scratches here. For the SUBA 4 step, the material removal rate was 2 microns an hour, and the SA was 58 nanometers, and the SQ was 72 nanometers, and the SC was 450 nanometers. Again, there is this damage being introduced by using this type of pad here, where we had these circle defects. And then lastly, we tried the Polytex, which had a material removal rate of 3.23 microns an hour. And this one, we saw an improvement in the surface, where the SA went down to 1.56 nanometers, the SQ to 1.9 nanometers, and the SC to 18 nanometers from 50 from the previous step. So this pad was what we determined would improve the surface and be the one we would go with going forward. So after we figured out what pad to use for the quarter micron aluminium step, we wanted to look at process optimization. So we started off with that 0.1 psi, and then we tried 0.3 psi, and we saw that the material removal rate doubled at 0.3 psi versus 0.1 psi. There was not a significant difference in surface quality again. So material removal rate was 6.47 microns an hour, and for the 0.3 psi, and for 0.1 psi was 3.23 microns an hour. And for the surface roughness, the SA was 1.58 nanometers for 0.3 psi versus 1.62 nanometers for 0.1 psi. So about the same, as well as for SQ, we saw 1.99 nanometers for 0.3 versus 1.72 nanometers for 0.1 psi. And then for SC, got 18 nanometers for 0.3 psi and 16 nanometers for 0.1 psi. So for comparison, we also wanted to see if there was any advantage of if we would get finer surfaces if we tried the alumina suspension without diamond. So it'd be just alumina as the abrasive. So that's what this comparison is here. So on the left, we have 0.3 or 0.25 alumina with this was at the higher pressure of 0.3 psi, where the material move rate was 6.47 microns an hour. And then on the right, we have without diamond, and the rate was 3.82 microns an hour. So there's definitely an advantage with the rate when you use the diamond. And then the SA was in the surface roughness in general was about the same. So for SA it was 1.33 versus 1.326 nanometers for SA, and then SQ was 1.679 versus 1.629, and then for SZ it was 14.3 nanometers versus 11.2 nanometers for the surface roughness. So based off these experiments, we found that the final process that was optimized for calcium fluoride was you would start off after grinding, going into a 3 micron alumina gem on MHS at 1.6 psi, where your material removal rate would be 30.7 microns an hour, and you would need to remove about 20 microns of material, where you would go from a ground surface of around 300 SA to a 5.6 SA surface. And then after that, to get a finer surface, you would do a 0.25 micron alumina gem on politics at 0.3 psi, and your rate would be 6.47 microns an hour, and your SA, you would end up with 1.33 nanometers. So key takeaways we found in this study was that based on the literature, we assumed that the lower pressures would be needed to process calcium fluoride, but we actually found that the higher pressures for both these process steps did not result in higher surface roughness and yielded better rates. And the alumina gem suspension with diamonds was faster than the same formulation without diamonds, leading to an equivalent surface roughness. So there is a lot of value with having this alumina diamond suspension. And that is my presentation.
Thank you so much, Caroline, for joining us to help viewers overcome the processing and polishing challenges of calcium fluoride precision optics. To everyone that's joining us in the audience, if you haven't already, you can type your questions and comments into the Summit chat box, and do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Optical Fabrication Summit. Thank you all so much for joining us.